Hello everyone. Today I would like to take the idea of numbers further in the form of what is called a number line. This line will allow me to represent any number I can imagine, starting from 0. And then I can say, okay, this is 1, this is 2, and so on. This is -1. You see, when I start taking differences, so difference can be positive as well as negative, so on. Then, if any ratio or any magnitude requires me to go to find a number between these two, I can say, okay, this will be 1.5. Yeah? So this will be 1.5. Similarly, if I go there, yeah, so it will be 1.5 and a half of a half. So I can say it will be, so this will be 1.5, because we see 1.5, and this will be 1.5 and a fourth, and so on. So another way of looking at this is that if I have, for example, a length, and if this represent 1, yeah, this 1 could represent 1 meter, 1 kilogram, 1 degree Celsius, or anything you can imagine. So I just write 1 for that, and then this will be 2, yeah? And this tiny part, I can say, okay, it is, let's say I say that this is 1/3 of 1, so this will be, this whole thing will be 2 plus 1/3, yeah? Claiming that this is 1/3. Now, things could get complicated when you zoom in, and maybe you have to add more fractions. So let's say that I have some length, and then to write that length in numbers, let's say I need 2, and then I need, let's say, 1/3, and it turns out that, okay, if I want to be accurate, maybe I need 2/5, and I need 7/11. So there are two possibilities. Maybe I get to the bottom of it, and there is a stage where I stop and I say, okay, that's the exact representation of this length. Whenever that is possible, and remember I have all different choices, I can safely say that this length or this magnitude, could represent any magnitude, can be, because if I simplify all these numbers, provided they stop, I will be able to represent this by a ratio, where I will have some number in the numerator, some integer, and some integer in the denominator. You can try a few examples, and whenever this stops, you will be able to write. No matter how large these numbers are, but you can say that, okay, so your claim seems to make sense, that I can represent any length, any magnitude, as a ratio of two integers, positive or negative. So the next question, and maybe, I mean, if you don't want to think in terms of length, I can give you another perspective so that you don't seem limited. These numbers could also represent, for example, areas. So when you want to find area, you can come up, let's say this is your unit area. Yeah, so unit area means that this side is 1, this is, and this unit area could represent some quantities. It could represent an area, it could represent any other quantity. And if I say, okay, for some areas I will need 2 units, so the area will be 2. Maybe I need 2 units and half units, so the area will be, this area will now be 2, because 1 plus 1 plus half. And maybe I say, okay, maybe I need some other fraction, so 1/3, and so on. Whenever this stops, I can say, okay, I can represent any area of any shape as a ratio between 2 numbers. And if I'm talking about difference of areas, when I compare 2 areas, I can get negative numbers. So somehow you start having this belief that I can represent any number I could ever need by simply dealing with ratios, positive or negative. If I allow positive, both positive and negative ratios, so I have a complete set of numbers, and any number that can be written as a ratio of 2 integers. There is even a name for that called rational numbers. So it looks like this number line has all the rational numbers. But the question now comes, are there points in this number line which are not rational numbers? Another way, that if I start populating this line with all rational numbers I can imagine, tiny, tiny fractions, are there holes in this line? So in other words, can I find, for example here, a point which will lie on this line, but without any representation like that? If such a number exists, that will be, if this is rational, that number will be irrational. Now the question is, do I have such numbers? So it turns out that the answer is yes. Yes, if you think of this line as a continuous line, without. So imagine if you have a pen, and if you start moving, and if you imagine that, okay, the pen is so perfect and the surface is so perfect that you will never have any holes. Now this is of course an abstraction. We'll get to that later, why that is not a very sensible imagination. But let's assume that I have a full line. So it turns out that yes, there are points which are irrational. So let me give you an example. So the first example is, say I imagine a square, and I don't know, of course, all the sides are equal length, and I don't know the lengths of these sides, but say I know the area. So if the area is 2, what should be this side? Of course, in other words, what should be every side? So if there is such a number, we represent such a number by, because I need to remind myself that I am talking about 2, and I introduce a symbol, this symbol. This symbol just tells me that any number, if 2 is under this symbol, then I will have an area of 2. Of course, you can come up with any other representation, but this is standard. Yeah. So people call it the square root of 2. Yeah. So it's like you are squaring this to get 2. So if you undo that squaring, yeah, if you undo that squaring, you get. So I can simply say what it means is squaring undone. Yeah. Squaring of squaring undone. Yeah. So first let me give you some numerical attempts of trying to represent this number as a ratio. So it turns out that there are some attempts. If I want to write this, yeah, so some good approximations are, of course, your first attempt will be simply 1. Yeah? So if this is 1 and if this is 1, 1 times 1 is 1, but of course the area is 2. So it's not a very good approximation. Of course, it is an approximation. It is close to this. Another approximation is half of 3. Yeah? Half of 3 is actually 1.5. So if this is 1.5 and this is 1.5, and if you calculate the area, that area will not be 2, but it will be closer to 2. So another approximation is 7/5. Yeah? 7/5 here, 7/5 here, multiply. You get an area that will be close to 2. Some areas could be a little larger than 2. Some areas could be a little smaller than 2. So if you want to visualize the result of these approximations by rational numbers, by ratios, some of these will be a little smaller, yeah, and some of these will be a little larger. So the next one is 17, 12, and so on. You can actually Google this and you will come up. It turns out that no matter how many times you attempt, you will spend the rest of your life doing this, and every time the result will either be a little less than 2 or a little more than 2. Yeah? You will get closer and closer to 2, but don't expect that you will ever reach 2 exactly. So numerically, you can establish that there is no such ratio. There is no such ratio. Let me give you another example. And that example is of a circle. Let's say you have a circle, a perfect circle. And let's say the area of that circle is the question, and let's say you know the radius. The radius is 1 unit. Yeah? So if the radius is 1 unit and you have a circle, the question is, what is the area? Yeah? And if I can calculate this area, let's give it a name because this is a unique circle. Yeah? There is only one circle with this special radius, 1. So I can fix this and let's call that, yeah? This is called pi. Pi. P-I. So, and the idea is to find a rational number equal to pi. Yeah, let's try that. So, how you go about it, your first attempt will be, maybe you think of it as a square. Yeah? So this is 2, 1 plus 1. This is 2, 2 times 2, 4. So your first attempt will be 4. Of course, this is wrong. Yeah? Your second attempt will be some square inside, yeah? And then you can come up with other approximations, yeah, like this, yeah, or like that. You can try different things. And let's say you are clever enough to calculate all these areas. Let me just write a few results. The next thing which is even better than 4 is 3. But of course, it turns out that it's not exactly equal to this area of a circle. The next of a circle of course, the radius 1. The next approximation, which is better than this, is 22/7. Of course, this is a ratio. The next is 333/106, which is better than that. The next is 355/113, which is better than that. And let me just write one more number. Of course, you can search Google and you can find many such numbers. 993, yeah, it's a huge number. And this is the denominator. Again, you can spend the rest of your life trying these approximations. These ratios will get closer and closer to pi, which means the area of a circle. But again, you will never reach the exact area of a circle of that radius. Some of these ratios will be a little larger than that number which you are looking for. Some of these ratios will be a little lower than that number. So it turns out that we found two examples. Let me just remove this. Of course, these are not the only two examples, but you found two examples. One is the square root of 2, or you can also call it 2 under the radical sign. And the other number you found was pi, the area of unit circle. Of course, there are many other numbers, but these two are enough to answer this question: are there any holes in this line? If we only limit ourselves to rational numbers, to ratios of integers, the answer is yes, because these numbers will fill in. So we have established that the number line is not complete without such numbers, such irrational numbers. And there are many irrational numbers like that. So we can now say that, okay, let me now coin a new terminology. This number line is actually called the real number line. So we now have a set of numbers which we call real numbers that can be represented on a number line or real number line without any limits. And it can be filled with two types of numbers, with ratios, which we call rational numbers, and with numbers which cannot be represented as ratios, and they will be called irrational numbers. So if I take rational numbers and irrational numbers together, I have every real number. Real means that any number which I can imagine or need in calculations. In calculation of magnitudes, in calculation of multitudes, ratios, differences, comparisons, any areas, volumes, temperature, pressure, length, anything, mass. So next time I would like to convince you more logically why these two numbers are irrational. Because today, because of the time limitation, I limited myself to numerical illustrations. We'll deal with this issue next time. So wait for that, and bye for now.